host, you take that application data, and remember layer 7 we said was going to, for example, be implementing HTTP. So you will add a layer 7 header to that application data. You'll add an HTTP header. This is what allows the HTTP peer on the other side to understand what that message is. You'll then hand it down to your layer 4 implementation, or TCP. TCP is going to put its own TCP header on top in addition to that HTTP header. And then pass it down to the IP layer, or L3, which is going to put an IP header on top. Okay, and down to the L1, L2, which is your data link layer, and getting the bits out on the wire. And then when you send this message along the way across to the other end, L1, L2 is going to look only at the data link layer header, knows what to do with it. It's going to then take it off, send it up to the IP layer. IP layer is going to look at the IP header, send it up to TCP, and so on up till you get to the application layer. Okay? So that header is what allows these peer implementations to talk to each other. And if you look at each of these layers, it's only looking at the header that's relevant to itself. So the data link layer never looks at the HTTP header, for example. The IP layer is not looking at the HTTP header. It's only looking at the information in that IP header. We haven't yet talked about what goes into those headers. That's what we'll be doing over the semester. So packets contain multiple headers. If you actually went and looked at a packet on the wire, it would have all of those headers stacked one on top of the other. Is that making sense? Yep. Mm-hmm. Yeah, so I don't have, just to not make this diagram even more complicated, I don't have the router here. What the router would do is exactly the same as the end host. When it receives the full packet, it would, the Ethernet, going back to our previous example, the Ethernet implementation would look at the Ethernet header, and then it would say, okay, I'm done. This was the Ethernet destination. So it takes off the Ethernet header, hands it to the IP layer. The IP layer would do what we've talked about in previous lectures. It would look at the destination IP address, that's the address of the end host, would look it up in a table to know which interface to send it back on, and then send the message back down to the optical implementation. Okay? It would never look beyond the IP layer header. So it never looks at a TCP or an HTTP header. Got it? Any other questions? So here's an exercise, and you'll be doing this in the discussion section as well, is take the previous slide where we were adding and removing headers, and think about this physical path through this complicated protocol diagram. And ask yourself at different points in this path, what headers do you expect to see on the packet? It's a great exercise by which to make sure you're following all this. So for example, if I told you the IP implementation at this first router, what headers are on the packet and what header is that module looking at? The answer in this particular case would be that the packet at that point has no L2 header, has no data link header. It does have an L3, L4, and L7 header. So it'll have an IP, TCP, and HTTP header. But it's only going to look at the IP header, the L3 header. Yep. Yes. They would be routing on different headers. This is a subtlety that I think will be clearer when we get to Ethernet. The Ethernet, if I had two Ethernet, and I actually have this example right here. If I had two Ethernet switches side by side, they would be looking at Ethernet addresses and deciding to go out to the next interface. They would not be looking at IP addresses. Right. Yep. It depends at which layer. At this point in the router, yes, it would have all the headers. You would take off the Ethernet header. So if we go back to here, if you look on the receiving side, as you move up the stack, you're taking off headers. Yeah. So at this point, you would have the Ethernet header. You would take it off. At this point, there's no Ethernet header. When you send it back here, this interface adds a sonnet. Oh, I have sonnet here. Sorry, that's the precursor to OTN. A sonnet header. Yep. No. Right. So if these were both Ethernet, so let me go. I have these slides to explain a historical side note, and then I'll come back to your question, which is, we've said switches and routers are the same. Don't worry about it. Historically, the reason we had those different terms was that you could buy Ethernet switches, and Ethernet is the most common type of switch that we see in most deployments. You could buy an Ethernet switch that actually did not implement the IP header, the IP layer. It was just able to switch Ethernet packets. It has its own protocol by which you learn about paths through an Ethernet network, and it does this routing on Ethernet headers. And so we would call these switches, and the ones that actually implemented IP we would call routers. We don't follow this distinction anymore because at this point, you can go look at any Ethernet switch that's sold on the market. They also implement IP. Okay. So, yep.
Does IP have access to the transport header and chooses not to access it, or does it not?
It has access. If it wanted, those bits are there in the message it received. It's just as per the protocol, it should not be looking at the TCP header. There are violations of this in practice, but the protocol, IP protocol, does not require you to look at the TCP header. Yep. It doesn't. It can only get you across an Ethernet network. The minute you try to leave the Ethernet network, it doesn't know what to do. Then you need IP. Within one Ethernet network, which is defined as a set of interconnected Ethernet links, you would run an Ethernet routing protocol, a spanning tree or some more modern form of Ethernet routing, which we haven't covered yet, so you don't have to know. So I'm going to continue in this class to use switch and router interchangeably. Just wanted you to know where that distinction comes in. So review, we're kind of done with our top-down view of how the internet works. As you can tell, this concept of layering and adding headers and so on can get pretty tricky, so make sure you understood it. We have these 5 layers. All 5 of them are implemented at end hosts, and only 3 of them are implemented in the network. Before I move on, any last questions on that? Yep. This is a question, does every header have the same size? No, not necessarily. It depends on how that protocol is defined. So IP, for example, has something called IP options that could make the header be different in length. But you have to know how to, as an IP implementation, you have to know how to figure out what the length of your header is. Any other questions? Okay. Let me take a 2-minute break, and then we'll continue on with the question I want you to think about is, why is this particular assignment of tasks good? Right, so we've said this is the breakdown into layers, and we've said typically the end hosts implement all 5 layers, the network only 3. We're going to take a more philosophical look at this now to talk about why that particular partitioning has been very useful on the internet. Okay, let's continue, and I'm going to try and do a speed end-to-end principle in 20 minutes. So let's try to make this work. So the question of why is this assignment a good one? And a lot of what we're going to be talking from here on, the kinds of lessons and terminology we use, comes from someone called Dave Clark. He was the chief protocol architect for the internet back in the 80s. So back in the 80s, there was this committee called the IAB, the Internet Architecture Board. They were not a standards body, but they were there to offer architectural guidance to the people developing protocols like TCP and IP and so on. And Dave Clark was the chief protocol architect there. So he's not the person that invented TCP, IP, BGP, but he's very much the person that gave us the language and the rationale for why the internet works this way. And so there are two papers in particular that are classics. When you take a PhD level class on networking, these are the first two papers, every class I know of, these are the first two papers that you'll go read. They're both beautiful papers. They're actually very accessible. If you want to go peek at them, there's a link at the bottom. The second paper, which is the design philosophy of the internet protocols, is the paper we're going to be reading later in this semester. Okay, so I'm going to cover kind of the argument that is in his first paper, the end-to-end arguments paper. I'm going to do a first pass through trying to explain what the end-to-end argument is. We're going to come back to it much later in the semester, because I find when you've actually understood routing and TCP in more depth, then you better appreciate what Dave Clark is trying to say. So we're going to do a first pass now and an in-depth view of the end-to-end principle later. So what does the end-to-end principle mean? It's a guideline. It's not a rule. You don't have to follow the end-to-end principle. But it's a guideline that guides the debate about what functionality gets implemented where in any distributed system. So it's actually a fairly general rule or general guideline for how you should be partitioning and assigning tasks to different pieces in a distributed system. In this class in particular, we are going to be thinking or using it or thinking about the functionality that a network should implement. What does the end-to-end principle tell us about what the network should or should not implement? Even one step more specific, we're going to be thinking in this lecture about should the network implement reliability? Okay. Should it be the job of the network to worry about reliability? So before I even go there, what does it mean, or what do I mean when I say that the network should implement reliability? You could implement reliability in a number of different ways. I'm going to give you one just so you have a mental picture. The idea is that the network is going to do a little extra work to make sure that the packets it's trying to send are getting to where it's trying to send them. It's not just going to send it out and hope it gets there. So for example, typically what this would mean is something like router 1 will send the packet to router 2, and then it'll wait for an acknowledgement to come back from router 2 saying, I got this packet, you can now send me the next packet. And it'll not just be I got this packet, it's actually going to send something like a checksum. Is everyone comfortable with the idea of a checksum? Yeah. So it's kind of like a hash or fingerprint that says this is the actual content I received. So it's going to send that checksum back to 1. And so then 1 can say, will know that yes, 2 received the packet, yes, it received the correct packet, and yes, I can now send the next packet. This is actually what the first iteration of the ARPANET, which was the first iteration of the internet, implemented. And you're going to do this repeatedly at every link. So this would be one example of a network that's trying to implement reliability. If it did not get that ACK back, it would resend the first packet. And maybe it would resend it 5 times or so. And just to set the stage, there is nothing we can do to guarantee 100% reliability in all cases. Right? If I have a, heaven forbid, a nuclear attack that takes out half the internet, I'm just not, there's no path between A and B, I'm just never going to be able to send a packet to B. Or if B crashes, I'm not going to be able to get the packet to B. So we're not talking about 100% in all possible cases reliability. We're talking about things the network can do to increase the chance that your data will get there correctly. Okay, and so the question we have at hand for the next 20 minutes or so is, what do you think? Should the network implement reliability? Is it a good idea or not? And to frame that thought, here's an example that Dave Clark uses, which actually came out of there when they were building these systems, which is, let's say that the task I have at hand is to do a pretty good, reliable transfer of a file from host A to host